Hello and welcome back, everyone. Today I'm going to be talking about a proof as to why the derivative of sine is equal to cosine. This is the first of a three-part video. In the second one, I'll talk about the derivative of cosine. Third one, we'll talk about the derivative of tan. But this first video is really important. I'm going to use it for both of the other two videos, so this is really the most important one of the three. So what we're going to use for this proof is two smaller proofs, and I'm going to call them here lemmas. So a lemma is basically a smaller proof that's used inside of a larger proof to support that proof. So it's fundamental. So before we can prove that the derivative of sine is cosine, we first need to prove this lemma here, that the limit as h goes to 0 of sine h over h is going to be equal to 1. And in order to prove this first little lemma, so we're just focusing on this for now, we're going to construct a unit circle. So as we remember, or hopefully as we would remember, if we have a unit circle, so let's say that's the circle there, just imagine it's a little bit more circle shaped, we can consider that the y-coordinate of a point that lies around that unit circle, and remember when we talk about a unit circle, what we mean is a circle of radius 1, right? So if we look at that triangle there that I've just drawn in black, we can see that the hypotenuse is equal to 1, so it's the hypotenuse, and the opposite side is equal to sine x. Now, why is the opposite side equal to sine x? Well, if we remember our acronym, which is SOHCAHTOA, we have here that sine is equal to opposite over hypotenuse, so sine of, in this case, x. So sine of x is equal to opposite over hypotenuse. We can see that opposite is equal to sine of x. That opposite is equal to, well, whatever this side is, the opposite side. The hypotenuse is equal to 1, so sine of x must be equal to the opposite. So we can see that sine of x is equal to opposite divided by 1, so therefore sine of x is equal to the opposite side of that right triangle, right? So that's how we've labelled the y-coordinate of that point around the unit circle as sine of x. And by the same token, if we were to, I'll just get rid of this and just kind of look at the larger triangle here, so this triangle right there, if we were to consider that triangle, just bear with me, that bottom length, so if we consider this as a giant right angle triangle with this angle here x, we can see that the adjacent side is equal to 1. Because this is a unit circle, so the distance from A to B, that radius down there is the radius of the circle, so of course it's just equal to 1. And if we consider the tangent ratio, so we remember that tan is equal to opposites over adjacents, we now see that the adjacent side is equal to 1, so we have that tan is equal to O divided by 1, so opposite divided by 1 is just opposite, so tan is equal to the opposite of that larger triangle, so that's why we've labelled that as tan there. Okay, so what we're interested for this proof is the ratio between sine of h and h as h approaches 0. So in this case, I guess let's just change that h to an x. So we're interested in as sine of x divided by x as x goes towards 0, so as this angle here goes towards 0, what is going to happen to that ratio? So we need to consider how this occurs if we're approaching 0 from the top or from the bottom. So we could actually take that triangle and imagine it extending down like so. So we're interested also in this triangle down the bottom here, right? So if we take that point there, try and do this a little bit better, so I know it's not a perfect circle there, but just imagine that x, right, that x is an angle, by the way, we're interested in x approaching 0 from the top, which is from this from the perspective of this blue triangle here, and also from the bottom. So just keep in mind, what we're going to have to do is we're going to have to do this, the same sort of maths that I'm about to show you, to the positive blue triangle, and also if x is a negative angle. But let's, for now, just simplify this, ignore the whole larger triangle, and just focus on this triangle as is. So just focusing on that blue triangle, okay? So here's the idea. what we need for this proof is to consider a few different little shapes. So we've kind of got this little diagram here. We've kind of got an understanding of how this might work. I want us now to draw attention to this red triangle that I've highlighted here for you. And what is the area of that red triangle? And I've just kind of like drawn a little picture of a triangle next to it there. Now, based on our understanding of Year 8 mathematics, we should know that the area of a triangle is half base times height, right? So we have the formula half. Now, what's the length of this base here? Well, the length of that base is just equal to 1. So it's half times 1, and the height we can see here is sine h, or sine x. We've changed all of these to x's. It's a little bit confusing, but bear with me. So we've got half sine x. Okay, so that's just equal to a half of sine x. Beautiful. Okay, now let's consider another shape on this diagram. This time I want us to consider the shape that's actually been drawn for us in this blue color. So I'll try and stick to that blue color. We've kind of got this blue wedge. Now, it's sort of like a portion of the overall circle. So I believe we call them sectors, or might be segments. I can't remember. Anyway, the point is we've got that little wedge there. So what's the area of that wedge? Okay, so let's think about that wedge. What we have here is kind of like a fraction of the overall circle. So if we imagine that the overall circle, it has a total number of radians of 2 pi radians, right? So we've got x fraction out of the 2 pi radians, right? So that is going to be x out of 2 pi times the area of a circle, the area of the overall circle. Now, just to understand why that might be the case, if we were looking at the quarter circle, right, that would be well, that would be pi on 2 radians, so 1/4 of the overall circle. So pi on 2 divided by 2 pi, that would be equal to 1/4. But in this case, we don't know what x is, so we have x over 2 pi, that fraction of the overall circle. Now, what is the area of a circle? Well, the area of a circle is going to be, in this case, if we recall, area of a circle is pi times radius squares, and the radius of this overall circle here is going to be equal to 1. So therefore, we would find that the area of this wedge is going to be x divided by 2 pi times the area of the circle, which is going to be pi times 1 squared, because the radius of this unit circle is just equal to 1. So that is going to leave us with x over 2 pi times pi, and we're going to have a pi at the top and a pi down the bottom, so they are conveniently going to cancel out for us, and we're just going to be left with the area of that wedge is x divided by 2. Fantastic. Okay, one final shape that we need to consider. We want to look at this larger triangle right here. Okay, so this larger triangle right here, and work out what the area of that triangle is. So what's the area of that triangle going to be? Well, the area of that triangle is going to be half base times height. So we can see that the length of the base is equal to 1, just like we had before. And this time the height of that triangle is tan of x. So therefore we can see that the area of that larger triangle is half tan x. Okay, so we can kind of put this all together now. What we can see here is a little bit of a hierarchy in terms of size of these shapes. I don't think there would be too much debate in me saying, that the area of that larger triangle is in fact going to be larger than or equal to the area of this wedge. The area of this wedge right here. And that wedge is clearly larger than or greater than or equal to the area of the red triangle, right? So just consider what I'm saying here. The large green shape, that's clearly larger than the blue shape, because the blue shape is contained within the green shape, and also the red shape is contained within the blue shape. So we've got this hierarchy of sizes. So if I substitute in those areas, we're going to get, well, the area of the blue shape is half tan x, and we know that that's going to be greater than x over 2, and we know that that's going to be greater than half sine x, just substituting in what we know these areas to be equal to. We can then neaten this up a little bit. First up, we can see that in each of those, every side of that inequality has a divided by 2, so we can just to multiply everything there by 2. That's going to give us tan x is greater than or equal to x, which is greater than or equal to sine x. That neatens things up a little bit. We can also recall, I'll do this over here, recall that tan of x is equal to, I think it's sine x over cosine x. So that comes from opposite over adjacent. This is just one of the trig identities that we know from last year. So we have tan of x is equal to sine of x over cosine of x. So we can just go ahead and replace that in this expression over here. Sine of x over cosine of x is greater than or equal to x, which is greater than or equal to sine of x. We're also going to, because what we want to end up with, by the way, is this guy here, sine of x over x in the middle. We're going to do a little bit of a manipulation here. What I could do is I could flip each of these fractions. So just recall, if I flip this, so for example, if I flip this and this, which is the same as raising both of them to the power of -1, I'm also going to have to flip the inequality sign. So we can see here that if x is greater than or equal to sine of x, then 1 over x must be less than or equal to 1 over sine x. And in the same way, I can flip this other fraction over here, so we could have that's going to be greater than or equal to cosine x over sine of x. All right, and finally, I'm actually going to multiply all of these sides of this inequality by sine of x, and that's going to give us the following expression, because sine of x cancels out. Sine of x over x is less than or equal to 1. Okay, there we go. So, believe it or not, we are actually almost there. So now we have that cosine x is less than or equal to sine of x over x, which is less than or equal to 1. Now, there is this idea in calculus called the squeeze theorem, which says that if cosine of x is less than or equal to sine of x over x, which is less than or equal to 1, then the limit as x goes to 0 of cosine of x is less than or equal to the limit as x goes to 0 of sine of x over x, and that's less than or equal to the limit as x goes to 0 of 1 by the squeeze theorem. It's called the squeeze theorem. You don't really need to know that. But yeah, it should be fairly intuitive just kind of looking at this, that oh, sorry, that's not the squeeze theorem, but we'll use the squeeze theorem later. But it should be fairly intuitive looking at this, that the limit as x goes to 0, that if cosine of x is less than or equal to sine of x over x, which is less than or equal to 1 over 1, then their limits as x goes to 0 will follow that same hierarchy. So if we consider each of these, we should know that the limit as x goes to 0 of cosine of x, well, that's just basically going to be cosine of 0. And cosine of 0, if we consider the shape of the unit circle, cosine is the x-coordinate of a point on that unit circle. So as that angle approaches 0, the x-coordinate is going to be equal to 1. So you can type that into your calculator if you like. The cosine of 0, that's going to be equal to 1. So that's just going to give us 1. Okay, and if we consider this other thing over here, the limit as x goes to 0 of 1, well, 1 is not dependent on x. So as x goes to 0, 1 is just going to stay as 1. And finally, we have right in the middle, x goes to 0 of sine of x over x. And now what we're seeing is what I was referring to before as the squeeze theorem, which is that given that this limit that we're trying to resolve, the limit as x goes to 0 of sine of x over x, given that it is greater than 1 but also less than 1, it must be equal to 1. So this is the squeeze theorem. So this must be equal to 1 by the squeeze theorem. And again, you haven't heard of the squeeze theorem, but it should be fairly straightforward. If we have a number So like let's suppose there's some x. If that's greater than or equal to, if that's less than or equal to 1, but it's also greater than or equal to 1, well, the only possible thing that x could be equal to is 1 itself. And that's kind of what we found over here. So that proves our first little lemma here. We've shown what we wanted to show. So we've shown that the limit as x goes to 0 of sine of x over x is equal to 1. Okay, so we can draw a little square to show that we've done that proof. Okay, let's scroll down to the next proof. So the second thing we want to show, this is lemma 2, that the limit as h goes to 0 of 1 minus cosine h divided by h is going to be equal to 0. And for this one's actually a little bit easier than the first one. We're just going to start by writing it out. So we have here the limit as h goes to 0 of 1 minus cosine of h over h. Now, what we can do with a fraction like this, as we know about fractions, is we can multiply the numerator and the denominator by the same number in order to maintain equality. So, for example, if I multiply the top of this fraction by 1 plus cosine of h, and I multiply the bottom of this fraction by 1 plus cosine of h, the fraction should stay the same fraction. So if we go ahead and do that, we're going to get that this limit that we're starting out with is the same as the limit as h goes to 0 of 1 minus cosine squared of h divided by h times 1 plus cosine of h. Okay, so that's a nice little simplification there. We can then take this idea one step further. If we recall the Pythagorean identity, which is that sine squared x plus cosine squared x is equal to 1. This also comes from the unit circle, by the way. We could rearrange that expression and find that sine squared x is equal to 1 minus cosine squared x. So we've got that up the top here. We can now see that that numerator up the top of this limit must be equal to sine squared. So this is sine squared of h, or sine h squared, over h times 1 plus cosine h. Okay. Now, what we're going to do with this is another little bit of a trick. We're going to split this limit. How I mean by split it is I'm going to write it as the limits as h goes to 0 of sine of h over h multiplied by sine of h over 1 plus cosine of h. And the reason that we do this is just to make things a little bit easier, because you might notice that the first part of this multiplication is actually what we had in our first lemma, the sine of h divided by h, right? And we're allowed to do this because if we multiply the numerators here, we'll get sine of h times sine of h, which is sine of h squared. And if we multiply the denominators, we'll just get h times 1 plus cosine of h. So we haven't broken maths here. This is perfectly fine. What we are allowed to do with this limit is we can split it in half. So we can say, okay, the limit as h goes to 0 of this thing times this thing is the same as the limit as h goes to 0 of sine of h over h times the limit as h goes to 0 of sine of h over 1 plus cosine of h. And the reason that we do this is just to make our lives a little bit easier, because we now know that this is equal to 0. So the first limit is equal to, sorry, not 0. It's equal to, I think it was equal to 1, wasn't it? Yeah, so that was equal to 1 based on lemma 1. So by lemma 1. And then this second limit, let's consider this for a minute. As h goes to 0, sine of h, which is the y-coordinate of a point around the unit circle, sine of h is going to be equal to 0, and cosine of h is going to be equal to 1. So we're going to have 1 divided by 1 plus 1. So this is going to be 1 times 0 over 2, and 0 over 2 is just equal to 0, and then 0 multiplied by 1 is also equal to 0. So this is just equal to 0. And then we're done. So we've shown what we wanted to prove here. So we've shown that the limit as h goes to 0 of 1 minus cosine h divided by h is equal to 0. All right. And now we are finally almost there to proving what we wanted to show. So now that we've shown these two lemmas, we're going to use them in our final proof. So here's how the proof works. We want to show that the derivative of sine of x is equal to cosine of x. So we're going to start by letting the function f of x be equal to sine of x. Now, by the definition of the derivative, the derivative sine dash f dash x is going to be equal to sine of x plus h. So I'll show you every single step here. Let's not jump ahead a little too much here. So the definition of the derivative is that f dash x is equal to the limits as h goes to 0 of f of x plus h minus f of x divided by h. Okay, so we can see here that this is the same as the limit as h goes to 0 of, now f of x plus h is just replacing the x in sine of x with x plus h, so that will be sine of x plus h minus sine of x divided by h. Okay, so how do we deal with this? So this is just, substituting in the values into the definition of the derivative. Well, what we're going to need to know is actually something called the compound angle formula. So I'm just going to put this over here. I won't prove this one for you today, but we have the compound angle formula by the compound angle, or it's usually referred to as the compound angle identity. There's this rule that says that sine of x plus h is equal to sine of x times cosine of h plus sine of h times cosine of x. This is something that if you studied specialist maths, you would possibly remember this identity. So I'm going to just go ahead and substitute that into this limit up here. So we can see here that f dash x is equal to the limits as h goes to 0 of, and just replacing this part here, sine of x plus h, with what we have right here. We have, that's going to be equal to sine of x cosine of h plus sine of h cosine of x minus sine of x, all divided by h. Okay, now let's simplify this a little bit before we wrap things up. What we're going to notice here, potentially, is firstly, we can rearrange this. In fact, I should have just done this in the first go, but write it out like this. So we could rearrange this, have it as sine of h cosine of x plus sine of x cosine of h minus sine of x. I've just changed the order of the multiplication up the top there. Then what we can do is split the fraction just a little bit here. As we know, with fraction addition, it just means keeping the denominators the same and adding the numerators. We can do the same thing here in reverse. So this is going to be the same as the limit as h goes to 0 of sine of h times cosine of x divided by h plus sine of x cosine of h minus sine of x divided by h. So I've just split the two fractions in half. Similarly with limits, given that we know we're interested in the limit as h goes to 0, we can just kind of split this sum and write it as the limit as h goes to 0 of sine of h times cosine of x divided by h plus the limits as h goes to 0 of sine of x cosine of h minus sine of x over h. Okay. And finally, we're going to see if we can simplify these guys down. So if we look at that first limit, we can see that inside that we have sine of h and cosine of x. You might observe that cosine of x, x is not dependent on h. We can actually just take that outside of the limit and just write this as cosine of x times the limit as h goes to 0 of sine of h over h. And if we look at that second limit, there's a common factor to both those numerators, both of the denominators of sine of x. I'm going to take that out of the fraction as well. So that's going to give us sine of x times the limit as h goes to 0 of cosine of h minus 1 over h. And finally, we can sort of look at the second fraction there. It kind of looks almost exactly the same as our second corollary, our second lemma, which was 1 minus cosine h over h. So we can make things look a little bit better if we actually just make that a negative. So if I multiply the top here by -1, then that would give us 1 minus cosine of x. Cosine of h. So I'll just fix things up just a little bit, and you should see that what I'm writing here is the same as the line above it. If we take into consideration the negative sign, we have negative of sine of x times limits as h goes to 0 of 1 minus cosine of h over h. Okay, so putting things all together now, if we look at that first limit, and I'm going to underline it in blue, that is our first lemma. So based on our first lemma, we know that that's equal to 1. So this equals 1 by lemma 1. And now if we look at this second limit here, that, based on our second lemma, is equal to 0. So that's equal to 0 by lemma 2. So that tells us that this is equal to cosine of x times 1 minus sine of x times 0, which is just going to be equal to cosine of x, because sine of x times 0 is equal to 0. And we have finally shown what we set out to prove. So there we have the proof that the derivative of sine of x is equal to cosine of x. QED. Okay, so that was quite a long one. Next couple of videos should be much shorter if I manage to put them out. All right, thank you very much. Have a great day, and I'll see you next time.